I'm Simone Dalle Fabbriche, and today I will talk about my thesis, which is the analysis of the plasma discharge in a radiofrequency ion thruster. And my supervisors are Joey, Zhu, and Eduardo Aido. So first of all, what is a radiofrequency ion thruster? Well, let's start from the name. So it's an ion thruster, which means that it is an electrostatic device that uses an electrostatic field to accelerate ions to very high velocity. And it's radiofrequency, so it means that the plasma is sustained with a radiofrequency generator, so with an inductive coupling with the RF. With the Hall effect thruster, that was what Tatiana was explaining before, is one of the most mature technologies. So it has been used in several missions, and it is also now sold by several companies in different scales, different sizes. So why are they interesting? Again, it's an ion thruster, so this means that it has very high specific impulse compared to Hall effect thruster, but it also has a lower thrust to power ratio. That's why those thrusters are not so popular as Hall effect thrusters, and that's why I'm the unique one in our group studying those thrusters. Anyway, the very high specific impulse is the reason why these are very interesting, because for scientific missions in particular, where the propellant utilization has to be the maximum, I mean, the amount of propellant you use, you want to have the maximum thrust as possible, you want to use those kind of thrusters. So again, it's also radio frequency. So it has other benefits coming from these power deposition, which is basically a higher lifetime compared to the other ion thrusters, and also the possibility to be scaled quite easily. So to larger diameter and lower diameter. And here comes the objective of my thesis, which is trying to model and to understand the physics inside this kind of thruster with a aim to improve their performances. So first of all, let's define a bit how a radiofrequency ion thruster works. So we can divide the ion thruster into 4 different regions. First of all, we have a discharge chamber, which is the region in which the plasma is basically generated. Then we have the radiofrequency generator, which consists in an external radiofrequency generator and a coil which is wrapped around the discharge chamber, and the aim is to deposit the power inside the chamber. Then we have an acceleration system, which is composed by grids. This is the part common to all the ion thruster. And then we have the plume, in which we achieve charge balance with an external cathode. So it's very difficult to study this kind of thruster like as a unique piece. We need to split those into different regions, into all different components, and the way they interact with each other. That's the best approach to study those. First of all, for this presentation, I will just focus on the discharge chamber and the radiofrequency generator, which are the main things I'm dealing with. And so far, the state of the art for those kind of regions, is mainly consists in global models, which are DOD. They are very nice for companies because they are fast. They can be used in a normal computer, but they need very strong assumptions, especially for the distribution inside the domain and everything, and also other points. So instead, what I'm trying to do is to use our hybrid codes that are a good compromise between accuracy and computational time, but to simulate this thruster in 2D axisymmetric or 3D dimension. Well, this depends on the code I want to use. -N is 2D axisymmetric, while EP2+ is 3D Cartesian. But I will focus now on the 2D axisymmetric part. So first of all, I started to simplify the problem. So I just focused on the discharge chamber because it's a region that can give me a lot of information on how the plasma behaves inside the thruster. So I started avoiding the plume and the internalization region. I neglect the radiofrequency generator, so I am assuming a power deposition. And I've also neglect the acceleration surface. Instead, I've used a semi-transparent surface, which is a boundary condition that basically consists in a surface that can behave both as a material or a transparent surface. And this depends on a transparency coefficient that I can set. So having this, I obtain a cylindrical domain, basically, which has some particular boundary conditions. And what remains are a lot of parameters I can play with to understand the behavior of the cluster under different operational and geometrical conditions. I can also play with the physics of the cluster. So basically, I can play with the wall accommodation factor and the stepwise organization. But for this presentation, I will focus more on the first two parts. So the first thing I'm showing here are the 2D axisymmetric map of some of the main plasma magnitudes inside the cluster. The first thing we can notice is that, well, here I'm just increasing the power from 10 watts to 90 watts. Well, something I didn't say is that the thruster I'm studying is a small thruster, is a 4 centimeter thruster that works in this kind of range of power. And so we have that the uniform neutral density is not uniform at 90 watts. This means that global models that usually assume 0D values, so uniform values, cannot be used in these conditions. While in this case, they can be affordable. Then, okay. If we check the plasma density instead, we can see that the neutral density affects the plasma density. So basically, we have that the peak of the plasma density moves towards the injection region, which is here on the left, due to the high presence of neutrals. And this is something, again, which is against what global models predict, which is the shape that you can see here, which is quite different from the last one I'm showing. Finally, another thing we can see is that ions are mainly generated close to the main density point, but then they are accelerated towards the wall, which is a good thing for the right side where we have the grids, which means that we have a high beam current, but we also have very high wall losses because the ions are accelerated towards the walls and they are lost. Another thing I'm showing here is the effects of changing the mass flow rate. So here I'm showing the 4 of the main efficiency that the cluster has. So let's first start from the propulsive for the production efficiency. So we can see that production efficiency is very low, which this means that neutrals are basically ionized several times before having the possibility to exit the domain. If we check instead the utilization and the energy efficiency, we can see that the utilization efficiency, they behave basically in opposite behavior. We have that the utilization efficiency increases while the energy efficiency decreases with the power. And this, at the end, results in a thrust efficiency that presents a maximum point. And this maximum is also dependent on the mass flow rate, since changing the mass flow rate, so changing the line, we are moving the maximum point towards higher power. Now my actual ongoing work. So the results here are being collected with other parametric analysis that I didn't present, and they are now in a journal paper that is under review for plasma source science and technology. After that, I started working on the radio frequency generator. So I removed the assumption of the power deposition map, and now I'm letting the plasma I'm letting the radio frequency generator eating up the plasma. So here are some of the open questions we are trying to answer in this study, which is still preliminary. I don't have mature results to show here, but basically, one of the things we want to address is the residual magnetic confinement. So if you remember the slides I was showing before, here, ions were directly accelerated towards the wall. This happens also because we don't have a magnetic confinement that is something that usually plasma thrusters have. In this case, the magnetic confinement is absent, but we think that the oscillating magnetic field can behave as a magnetic confinement. And well, those are the achievements I have. I attended the International Electric Propulsion Conference in Toulouse last year, and I will hopefully attend the same conference this year in London with the results of the radio frequency generator. I have a paper which is now under revision, and for the future work, there is, of course, the implementation of the self-induced radio frequency generator model. and the analysis of the acceleration part, which is something that I was showing before in the 4 different regions. So that's something that we are still working on. Maybe if I have time also trying the simulation with alternative propellants, since those kind of thruster are actually used in several companies with air and iodine. Okay, so that's all.